Hello everyone, my name is Swaroop HP. I'm studying MTech in Thermal Sciences. I'm in second year. Today I will be discussing about the topic laminar and turbulent flow in fluid mechanics. Let us begin with the topic. First, we shall know what is laminar flow. Laminar flow is highly ordered fluid motion characterized by smooth layers of fluid flowing one above the other. So as we can see here from the figure, the fluid particles are moving in a well-defined path. So, and there are the fluid flow is in layer upon layer. You can see here there is no random motion of the fluid particles. So this is called laminar flow. Fluid particles move along well-defined paths or streamlines. It is also referred to as streamline flow or viscous flow. So this is called streamline flow because they move in a well-defined path, and also this is often called as viscous flow. Usually this kind of flow is observed in the fluids whose viscosity is high and which are moving at a very slow velocity. So example can be given as flow of highly viscous fluids such as oils at very low velocities. So as we know, oils have very high viscosity, so when they move at very low velocities, this kind of flow can be observed, laminar flow. So moving on to the turbulent flow. Turbulent flow is it is opposite to the laminar flow, wherein we can see the fluid particles are moving in a zigzag manner in a random motion, which is caused due to the high velocities in the flow, and also the wherever the viscosity of the fluid is less and the velocity is high, this type of flow can be observed. So the highly dissolved fluid motion that typically occurs at high velocities and is characterized by the velocity fluctuations. Here the fluid particle move in zigzag way, due to which eddy formation takes place. So as we can see here, the fluid particles are moving in a random manner, which results in the formation of eddies. So this eddy formation is often results in energy loss. In case of flow through a pipe or anything, this kind of turbulent flow will result in head loss, that we'll discuss later. Okay, now to identify the type of flow, we need a we make use of a non-dimensionless number called Reynolds number. So this Reynolds number is given as the ratio of inertia force to the viscous force. So Reynolds number is function of surface geometry, flow velocity, surface temperature, and type of fluid. Surface geometry in the sense flow is happening in a pipe or in a duct, or flow is happening over the flat plate, over a cylinder, like that. Flow velocity, it is the velocity with which the fluid is flowing. And surface temperature, here why we say Reynolds number is a function of surface temperature is most of the fluids, their properties vary with the temperature. So similarly the viscosity of the fluid also varies with the temperature. So viscosity, as it increases, so viscous force will increase. So viscosity as it decreases, the viscous force will decrease. So this viscosity is a function of temperature, so we say that Reynolds number is also a function of surface temperature. And also the type of fluid. Type of fluid is the density. Type of fluid means whether it is an oil, whether it is a air, what kind of fluid which is flowing. Like if it is oil, it has got more viscosity, and if it is air, it has got less viscosity, like that. So Reynolds number can be given as by the equation rho VLC by mu. So here LC is the characteristic length of the geometry, and rho is the density of the fluid which is flowing, V is the velocity of the fluid in meter per second, and mu is the dynamic viscosity. And mu by rho can be written as kinematic viscosity, so the other form is V into LC by nu. LC is the characteristic length of the geometry which is different for different kind of flow. For example, okay, I will discuss it in next slide, coming slides. Okay, and also the Reynolds number, as we can see here, it is the ratio of inertia force to viscous force. Reynolds number is high means the inertia force is high, the numerator is high. So inertia force can be high when the velocity and the density is high. So at larger Reynolds number, the inertia forces which are proportional to the density and velocity of the fluid are dominant relative to the viscous forces, and thus cannot prevent the random motion of the fluid particles. So when the inertia force dominates the viscous force, the Reynolds number will be greater than 1 and it will be higher. So in such cases, the random motion of the fluid particles cannot be prevented. And also at moderate and low Reynolds number, viscous forces are large enough to suppress the fluctuations and keep the fluid in line. So when the Reynolds number is low, it means that the denominator is high, that is viscous force is high. So when viscous force is high, it keeps the flow in a in line, like it maintains the flow in the laminar region. Next point is the intense mixing of fluid in turbulent flow enhances the heat transfer and momentum transfer between fluid particles, which increases the convective heat transfer rate. So one of the advantages of turbulent flow is that there is an intense mixing happening between the fluid particles in the turbulent flow. We saw here. So this results in higher rate of heat transfer during convection, and which is characterized by the higher heat transfer coefficient. Okay. For internal flow, for flow through pipe, Reynolds number can be given as rho V into dH by mu, where dH is the hydraulic diameter. Hydraulic diameter is given by 4 into AC by P. Here AC is the cross-sectional area of the flow and P is the wetted perimeter. So if it is a circular pipe, directly D is the internal diameter of the pipe. For DH is equal to D, we directly make use of rho VD by mu. So if the pipe is of any other cross section like square or rectangular duct, we make use of this formula, that is hydraulic diameter. AC is the cross sectional area through which the flow is happening. In case of square duct, it is A square. In case of rectangular duct, it is length into breadth, that is A into B here. And P is the wetted perimeter. Wetted perimeter in this case is, if it is assumed that there is no free surface, then all the sides are wetted. So it is 4A here. Here also 2 into A plus B, all the sides are wetted. In case of open channel flow, where there is a free surface, we need to make sure that only wetted perimeter is considered. For internal flow, the properties of fluid are evaluated at the bulk mean temperature of the fluid, which is the average of the inlet and exit temperatures. So in Reynolds number equation, whatever the properties of the fluid which we use should be taken at the bulk mean temperature of the fluid. So bulk mean temperature is the average of the inlet and exit temperatures of the fluid. Critical Reynolds number. Reynolds number at which the flow changes from laminar to turbulent. As I told earlier, Reynolds number is used to for checking whether the flow is laminar or turbulent. So the Reynolds number at which the flow changes from laminar to turbulent is called critical Reynolds number. For internal flow such as flow through pipes, flow is laminar if the Reynolds number is less than 2300, and flow is turbulent if it is greater than 4000. and if the Reynolds number is greater than 2300 and less than 4000, the flow is called transitional flow. Transitional flow is the flow which alternates between laminar and turbulent. So transition from laminar to turbulent also depends upon the degree of disturbance of flow. So as the Reynolds number is greater, if it is closer to the 2300 and greater than 2300, but it is closer to 2300, then there are, if the it can switch to the laminar flow, and if there is any disturbance, slight disturbance, and in the flow can switch to the turbulent. So that is the transitional flow. So transition from laminar to turbulent depends on the degree of disturbance of flow. So disturbance is usually caused due to surface roughness and pipe vibrations and the fluctuations in the flow. Okay, coming on to the shear stress and velocity distribution in pipe for laminar flow. In this figure we can see this shear stress distribution and also the velocity profile of the laminar flow. So velocity profile is parabolic in nature, with the value of the velocity increasing from wall to the center. So at the wall it is 0. At the wall it is 0 due to no slip condition. It goes on increasing and reaches maximum at the center. And shear stress distribution is linear, we can see here, and maximum shear stress is at the wall due to friction, and shear stress is 0 at the center. We will see the equations. Okay, shear stress at any radius is given by. So at any radius, if we want to calculate the shear stress, for example here or here, the equation used is tau is equal to minus dp by dx into r by 2. Here dp by dx is the pressure gradient at the given section. So this is the pipe. So at this section, what is the pressure gradient? If we want to know the shear stress at any point like here or here, so the dp by dx is the pressure gradient at this section, and r is the radius at which we want to know the shear stress. From the above equation, it is clear that the shear stress varies linearly with radius, since pressure gradient at any section is constant. So we can see from this equation, since pressure gradient at any section is constant, so tau is directly proportional to r, so which is a linear relation. That's why the shear stress distribution looks like this, linear variation. Velocity at any radius r is given by u is equal to u max into 1 minus r square by capital R square. So r is the radius at which we want to know the velocity, and capital R is the radius of the pipe. So this equation, we can see that this is a parabolic equation. That's why the velocity profile is parabolic. So from this equation, if we substitute r equal to r, that is at the center of the wall, that is when we want to check the velocity at walls, so we substitute r, so it becomes 0, and it is maximum at center, where at the center we take it as r equal to 0, so it will be u equal to u max. And also the average velocity, u average is the ratio of the total discharge q to the total area of the flow. So whenever we want to find the total discharge, we make use of u average. And from the derivation can be made to deduce the equation for u max, which is given by 1 by 4 mu into dp by dx into capital R square. Here again mu is the dynamic viscosity, dp by dx is the pressure gradient, and r is the radius of the pipe.